Okay, folks, we're back for part two of the tide notes. So hopefully you've done the worksheet up to this point on part one. And we're going to continue on into part two here. Just a quick review and making sure that it's all making sense here. Because it's tricky that this seems so simple, but then when we start putting it all together, it gets really confusing. There are two forces pulling on the water on Earth, pulling on all objects on Earth. That's centripetal force and gravitational force. And remember that gravitational force is usually stronger when you're a shorter distance away from another object than further away. And that centripetal force is a constant force parallel between the two objects. So all of these red lines indicate that the same amount of force is being pulled no matter where you're at on the planet between those two. And to get the overall net force, the resulting force, you take the difference between centripetal and gravitational. So you draw a line basically in your head from C to G, from this end to this end, and you end up with forces that pull this way, forces that don't do anything really, because it's just there's no difference between these two, and forces that pull this way. Over here, these forces would be this way. At the pole, the force would be this way, downward. At this pole, the force would be upward. So overall, all of the water on the planet is either getting pulled in or towards the edges, specifically the edge closest to the moon, and oddly enough, the edge furthest from the moon. And so those net resulting forces end up creating this thing called the tidal bulge. So I'm going to go back to here, and then we've got our tidal bulge. So there's going to be a bulge here and here if the moon is straight over here. But if we look down on this situation, what you'd find is that in this area, like right here on this edge, the water has moved towards this direction or towards this direction, and so the water is going to be thinner here. So if you've got a bulge, and remember it was a pretty narrow bulge, it was only like a foot or so, or 2 foot, maybe 3 foot. That water is going to be thinner here, and that's going to be your low tide, and this is going to be your high tide. So let's move on here. So keep in mind that the Earth rotates. Let's see here, I'm going to do that there. So keep in mind that the Earth rotates quickly, about 24 hours, right? So any location on Earth will rotate through that tidal bulge. So I'm going to go back up to this thing. So if you're in Africa, in a couple of hours, you're going to be facing the moon. And if you are facing the moon, then that tidal bulge is going to be towards you. So if you're on the coastline, that tidal bulge is actually going to be pulling here now. And it'll be loosening up on this edge because this edge has moved to the back side of the Earth. So you have to think of this in a dynamic system. The Earth is constantly rotating. So even though the moon is somewhat stationary, the Earth is rotating kind of quickly. And so the location of this bulge is dynamic. It changes throughout the day. So it rotates quickly, 24 hours. So any location on Earth will rotate through that tidal bulge. That creates high and low tide. So here's the moon again. There's the North Pole. We're looking down now. Here's a tidal bulge towards the moon and away from the moon. And then we have low tide along the edges here. So if you're on the planet over here or over here, you're going to have low tide. All right. But remember, at any point in time, you're still moving through. So if you're a person standing on the Earth here, within an hour or so, now you're over here. 2 hours later, 3 hours later, 12 hours later, you're back here again, you're back in a tidal bulge. Another 6 hours later, and I hope you get the idea that this is rotating. The moon is staying relatively still. All right, so speaking of that relatively still idea, lunar day, time between successive overhead moons is 24 hours and 50 minutes. It's not 24 hours. So why is that? Well, a day on Earth would be a 1 full rotation. But what is the moon doing in the meantime? The moon, keep in mind, and I'm going to zoom in on this thing quite a bit here. The moon, during the course of a day, is moving in orbit. Because remember, it moves in one day, it moves 1/27th of the arc of the circle. Because it takes, remember, from all the way back in like figure 1 or 2, it takes 27 days for the moon to get all the way around. So ultimately, in the 24 hours, so let's say you're standing here on Earth and you start the clock. 8 hours later, you're going to be over here. That tidal bulge is still going to be kind of there and there, but the moon has moved slightly because it's rotating, it's orbiting the Earth. 16 hours later, you're there. And 24 hours, you're back to the original spot, but the moon has moved on you. So to get the moon back straight overhead, in other words, to be right in the middle of high tide again, you need to wait an extra 50 minutes for you to spin into position where the moon is back over your head. That is called a lunar day then. So it's not just 24 hours, it's 24 hours plus 50 minutes. So hopefully that concept makes sense so that we have the idea that it's not just 24 hours because the moon is moving. And remember, the tidal bulge is always going to be facing either the side closest to the moon or furthest away from the moon. So that tidal bulge is moving too. Okay. Getting back to there. So that's what this writing says. An observer then should experience a high tide or low tide every 12 hours and 25 minutes. So let's think about that. High tide every 12 hours and 25 minutes. So if I zoom back in here a little bit. So if this person is at high tide right here, 8 hours later, about 12 hours later, they're going to be on the opposite side of the tidal bulge, but the moon has moved. So they got to be 25 minutes longer to be perfectly in the middle of that next high tide. So 12 hours and 25 minutes later, they've got another high tide. So in one day, in one Earth day, there are two high tides because you'll be in one high tide on one side closest to the moon, and you'll be in the other high tide furthest away from the moon. There will also be then two low tides because you're going to rotate through these low tide areas as well. All right. Get back to here. Why is that up? Okay. The time between a highest and lowest tide then should be about 6 hours and 13 minutes. So I'm not going to zoom back in here. But if you're down here and it is, whatever time of the day, 6 hours and 13 minutes later, half of the 12 hours and 25 minutes, you should be back into low tide. So this should take, from here to here, should take 12 hours and 25 minutes to get back to high tide again precisely. So half of that would be 6 hours and 13 minutes, give or take. Okay, so does that make sense? Now the diagram here and here, it doesn't have a sun in it. Well, the sun helps us understand what time of day it actually is. So the sun could be like over here, or the sun could be over here. The sun could be down below. It kind of depends on where the sun is as far as what time. So the moon tells us where the tides are going to occur, but the sun is going to tell us what time of day that's actually going to happen at. Okay. So we got to add back in the sun here. And first of all, one big concept is that if the sun is in line with the moon, like a full moon, you're going to end up with having more of a gravitational effect from the sun because it's in line with the moon. So it's actually going to help out the high tide. So it's going to make a larger tide or a tidal bulge when the sun is in line with the moon. That would be happening during a full moon or during a new moon. So look at these two pictures and recall your diagram from way up above here on the notes. I can go all the way up here. But remember, here we go. When the moon is directly between the sun and the earth, you get a new moon. And when it's on the opposite side, direct opposite side, you get a full moon. So during new moons and full moons, you have something that happens called a spring tide. So that's called a spring tide. I wish they wouldn't call it a spring tide because a spring tide implies that it just happens in the spring. But if you think about it, it happens every full moon, which should happen once every how many days? 27 days. So basically once a month, you're going to get a spring tide from a full moon, and once a month, you're going to get a spring tide from a new moon. So 2 times a month, you're going to get a spring tide. A neap tide is when the sun and the earth and the moon are at 90 degrees to each other. And the overall effect is that the moon and the earth the moon and the sun's gravitational pulls and centripetal pulls on the earth kind of negate, they kind of cancel out the overall effect of the tide. So what you end up with at that point then is a much, much less pronounced tide. It's really kind of a weak tide. So that's going to happen on a first quarter moon and on a last quarter moon. So when the sun is when the moon is 90 degrees from the direction or the position of the earth from the sun. Okay, so we got our moon here, earth, sun. That would be last quarter moon. And then you're going to end up with kind of a weak tide. There's still going to be a high tide. There's still going to be a tidal bulge, but it's really not going to be very much. Okay, so when the moon is in line with the sun's position, That's a spring tide. When the moon is first and third quarter, the sun's gravity lessens the effect. It's called the neap tide. Okay, think about how many times that would happen a year. Hopefully you can figure that one out. All right, so put it all together. Assume that the moon is in a waxing gibbous phase. So let's assume that the moon is in a waxing gibbous phase. What time of day now would you expect a high tide? Now remember, when we're talking about time of day, we have to think about the sun. We have to think about the position of the sun. So let's say the sun's over here. Light from the sun is over here. Waxing gibbous is over here. Where would our tidal bulge be? Our tidal bulge, and I'm going to try to, like exaggerate this. I can't draw on here very well at all. But our tidal bulge would be here and opposite of the moon, right? So always towards the moon or opposite of the moon. Now realize we've got time now because we've got a sun that's shining and lighting up this whole side of the earth, this whole side. The backside of the earth is in darkness because it's in the shadow of itself, basically. So we have dawn, and remember, we're rotating this way. So we have dawn, and you sit there and the sun comes up. But really what's happening is the sun is sitting still, and you are just rotating to meet the sun. So you are rotating to meet the sun. There's dawn. That would be like at 6 a.m. Let's just say it's 6 a.m. And then by noon, you are facing the sun is directly overhead. And then by evening, by twilight, 6 p.m., you're rotating away from it, and then you got midnight. So what time would it be when the moon is waxing gibbous directly overhead? That would be between twilight and midnight here. So what time is it between 6 p.m. and midnight? Well, that'd be about 9 p.m. So at 9 p.m., you'd have a high tide because the bulge would be here. That'd be at 9 p.m. What time would it be at low tide? At low tide, it would be over here because you'd tighten up over here and you'd tighten up over here. So we got our bulge here, and we're tight here, and we're tight here. Between midnight and dawn, well, what time is it between midnight and 6 a.m.? Well, that's about 3 a.m. You're going to get a low tide. So 9 p.m. high tide, 3 a.m. low tide, 9 p.m. or 9 a.m. Sorry, 9 a.m. high tide again, and then 3 p.m. low tide. I'm hoping that's all making sense. Now, if we change it to like a waning crescent, I'm sorry, let's make it a waxing crescent. Let's just choose over here. Now the bulge is going to be here and here. I mean, on this side. So then you're going to end up with bulges over here, low tides over here, and you should be able to get the time of day from that again. What if we change the position of the sun? You just have to keep in mind, where is it dawn and twilight and noon and midnight? So you put the sun over here. Midnight's going to be on the back side of the earth. Noon is going to be on the side facing the sun. So then you can set your time dial from where the sun is at. So you have to think about all those moving parts and the fact that you're rotating through things. Okay. So it gives you an idea of what the different, moon phases look like. And here's one: waning crescent, low tide in this diagram. So waning, how about a waning crescent, low tide in this diagram? The sun I put over here now. So waning crescent, that's here. That would mean that the high tide would be here and here on this side over here. So you got your bulges on both sides here. If the sun is over here, this would be noon facing the sun. This would be morning. This would be dawn. And this would be evening time because you're rotating counterclockwise. So this would be what, about 9 a.m. and this would be about 9 p.m. for your high tides, for both high tides, and then your low tides would be at 3 and 3. Okay, so hopefully that's all making sense to you. That's where we're going to end that. I've got a bunch of questions on your worksheet. If you have questions about how to fill them out or how to answer them, get in touch with me and we'll go through and we'll connect and make sure that you guys understand it. Thanks for your time.